This resource is the first in a 6-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation, and define 2 special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers solving exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. What is an exponent? An exponent is a shorthand way of describing a repeated multiplication. If we look at a problem like 2 raised to the third power, we recognize that it means to multiply 2 by 2 by 2. The 2 is called the base, and the 3 is the exponent. The base is what we are multiplying by itself. The exponent is how many times we do the multiplication. As another example, 3 raised to the 5th power means we multiply 5 copies of 3 by each other, which results in an answer of 243. We can combine exponents with the same base according to the various exponent laws. The basic idea of the exponent laws is for the mathematics to take a step backwards. When you multiply exponents with the same base, you really just add the exponents. We will explain exactly why this happens shortly. Dividing powers with the same base means we will subtract the exponents. When raising a power to a power, multiply the exponents. Any non-zero number or variable raised to the 0 power always equals 1. The final exponent law deals with negative powers. Negative powers do not mean negative answers. They mean fractions. Mathematicians prefer to never see negative exponents, so take the reciprocal of the power raised to a negative power and change the exponent to its opposite. Why exactly do exponents work in this way? Let's explore the multiplication law for exponents more closely. Suppose we have a to the third power times a to the second power. How can we approach this problem? Remember that a to the third really means a times a times a, and a squared really means a times a. So a to the third times a squared really means a times a times a times a times a. Counting how many a's are multiplying by each other, we find we are ultimately multiplying 5 copies of a, which is a to the 5th power. But we can get that 5 by adding the 3 and 2. Although this is not a formal proof, it does help to make more sense of the rules. A similar demonstration could verify the rules for division and powers raised to powers. A logarithm is the inverse function of an exponent. It is what undoes the exponent. If you have the exponent b, the base, raised to the c power equals a, the answer, then the equivalent logarithm would be log base b of a equals c. So the logarithm answers the question, to what power do I raise b to get an answer of a? Earlier, we looked at 2 to the third power, which would equal 8. In terms of logarithms, an equivalent statement would be log base 2 of 8 equals 3. For another example, suppose we had log base 5 of 625 equals 4. The equivalent exponent is 5 raised to the fourth power equals 625. Certain special logarithms are used more frequently than others. The first of these is the common logarithm, which is the base 10 logarithm. By convention, the common logarithm is written without a visible base. So if you see just log without a subscript, you can assume that it means base 10. Because it is used so frequently, scientific and graphing calculators have a log button to find the common logarithm of numbers. For example, log of 100 would be 2. One important feature of the common logarithm is that it is the inverse function to 10 raised to a power. This means that if you have the log of 10 to a power, the log and the 10 cancel each other out, and you are left with the exponent as your answer. For example, the log of 10 raised to the sixth power equals 6. When you think about the words that define logarithm, this makes sense. Log of 10 to the sixth means you are asking, to what power do I raise 10 to get 10 to the sixth power? This works in the reverse as well. 10 raised to the common log also cancels out. For example, 10 raised to the log of 51 would be 51. In words, this question asks, what is 10 raised to the power, which is the power to which we raise 10 to get 51? However, base 10 is not the only special logarithm. The other special logarithm is the logarithm with the base e, which is Euler's number. There are various mathematical definitions for e, but it suffices to say that it is an irrational number that is approximately equal to 2.71828. This constant shows up in many real-world phenomena. The log base e is called the natural logarithm, denoted ln. Like the common logarithm, scientific and graphing calculators have an ln button. As the natural logarithm is a logarithm, it is the inverse function for e raised to a power. Like the common logarithm and 10 raised to a power cancel each other out, the natural logarithm and e raised to a power cancel each other out. For example, the natural log of e raised to the 7th power would equal 7. As before, the reverse is also true. E raised to the natural log also cancels out. So e raised to the natural log of 206 would equal 206. We started this resource looking at exponents, defining the base and the exponent. We looked at the various exponent laws, which provide ways to simplify problems involving powers with the same base. We also considered logarithms, and defined them as the inverse function for exponents. We then considered how to translate between exponents and logarithms, as the base b raised to the c power equals a is equivalent to log base b of a equals c. We also considered common logarithms and natural logarithms, which are logarithms with the special bases of 10 and Euler's number e, respectively. But why do we need to understand logarithms anyway? One reason is that logarithms make calculations easier. Before the increase in use of scientific and graphing calculators, such higher-order operations as multiplication and exponents were much easier to perform by using appropriate logarithms. Another reason that logarithms are important is that they are essential for solving certain types of problems, which we will explore in a future resource. But for now, stay tuned to learn how to simplify logarithmic statements.